So we're going to look today essentially asking a question or answering this question. How fast are electrons when we think about them being inside of a circuit? What is, if we have our ammeter, we measure things, what is the actual speed at which electrons will travel around a circuit? What's a reasonable sort of estimation? And that's our aim, is to answer that. So we're going to sum up a few things that we want to say and want to sort of know. Okay, so in electricity or electrical circuits, we start by defining, and this is a bit of a recap on what we were talking about yesterday, the following. Okay, so charge is an inherent property of some particles. Things like electrons, ions, etc. It is measured in coulombs. Coulombs, and has the symbol Q. Okay, so that's a thing so that we have. So we have our charge, which is Q. Charge is quantized in units of the fundamental, and what we call it is the fundamental charge on an electron, which is written often as E. Okay, that's a thing. So that whenever you see a little E, it means it's charge on an electron. Where E is equal to 1.6 times 10 to the minus 19 coulombs. So if this is an electron, we'd say it's negative. So E just means that's the magnitude. Okay, so E just represents the magnitude charge. The charge on a proton is also E, but it's plus E, whereas charge on an electron is minus E. Okay, so and then so that's our charge thing. And we have current is defined as the rate of flow of charge. Okay, so defined as the rate of flow of charge. So anytime you have a movement of charged particles or charge anything from one side to another, you create a current. So if you lob like a metal, if you sort of lob a metal rod from one side of the room to another, you haven't created a current. But if you do that weird static electricity thing where you sort of rub a polythene rod and transfer a load of electrons to it, and then you throw that rod, that's a current. You've moved some charge, from one place to the other. So current is measured in amps, which is actually short for amperes. And is calculated via I is equal to delta Q over delta T. And if a current is steady, then you would just say total charge over total time. But often current fluctuates up and down. So when you turn on most appliances, there is a current spike. So things are constantly changing. So we tend to say when it's not steady, we would just do this we use delta Q, delta T. And then the final thing that we sort of had is that we sort of recapped is that we have these two things, is that by convention we say that current flows from positive to negative. So we would say the long side is always the thing, that's sort of the negative side. So by convention we would say that current is going around the circuit in this direction. Whereas in reality we know it's going the other way, but it doesn't really make a big difference. So by convention, current flows from positive to negative. Although, if you were thinking about a beam of electrons, they would be going the other way. So that, that's kind of summing up pretty much where we were at with GCSE, and we did see how, you can actually start calculating the number of electrons that, that is in, in a certain amount of charge, because you just do the number of electrons is equal to your charge divided by your total charge divided by whatever the charge on the electron is. So, for example, if you said, "Oh, I've got 24 coulombs," you just have 24 divided by 1.6, some 10 to the minus 19. You end up with a huge number. This number you'll get to use a lot. It's going to become very familiar to you. So we'll deal with that sort of later. Now, so that's kind of where we are. So let's consider a part of that weird circuit. Let's consider a bit of the circuit, inside this thing. Let's say it's a copper wire, and our copper wire is essentially made of, it's the way in which we say that things happen is that we've got our sort of positive ions. I really shouldn't have drawn this many because now I'm bored, and they're just all positive. And I think it's called the Drude model was originally where it came about, is to try and explain the method of conduction, is that each of these things is going to donate, through metallic bonding, is going to donate one free electron. So there's one free electron in these things. Now, what's interestingly, actually, I shouldn't really draw this line here, because this line doesn't exist. Because, everything's made of atoms. So there isn't really anything outside the wire. This is the copper wire. On the outside of it, you'll have an insulator, which will be some, some sort of other atoms, but they won't be donating any electrons. Okay, so that's kind of actually, that's when you hold up one of the chunky wires. This is what you're looking at. You're looking at something where there are no there's no free electrons, and then you've got a space where there is. There isn't really a line between the wire. So in metals, every conduction occurs because because of these delocalized electrons. Okay, and so you're never really asked to go into sort of this detail, but this is kind of what is going on. So in metallic bonding, each atom donates an average of one electron to the C of the localized ones. Okay, so that's kind of what's going on. Now, these free electrons, these are irrelevant to hold this thing together. These are not needed for bonding, so they're spare. And what they do is they move around quite rapidly, but randomly. They don't have a specific direction. Normally, they're flying around this thing sort of in a random sort of direction. So if we watched one of them, if we watched just one of them, we might see, if I just, have one there, if we were able to watch it, it'd just be doing this, going back and forth. And it's actually traveling very fast. Okay, so at this kind of random motion is really fast. It's moving at around 10 to the 6 meters per second. However, what happens is if we hook this up to a battery and we sort of, have this end being, let's keep it consistent. That end is negative and this end is positive. What will happen is instead, so let's do there, there. Let's give our things. What will happen is our electron will still have this really random motion, but over time, what's going to happen is it's going to drift in this direction, and that is what makes the current. Okay, so there's kind of two motions. There's this overall, like, there's this overall, like, sort of random motion, but that doesn't take it anywhere. There's no charge. That's just it moving around and being sort of odd. But here we've got a thing called what we like to call the drift velocity, and this is the thing we want to try and work out what it is. So it's the random motion is still there, but we sort of add to it a sort of a gentle drift to say, hey, go that way, go towards the positive thing. And the reason that works is that what happens is when electrons reach the positive start of the battery, they're basically becoming part of a chemical equation, which means that they get accepted into, they get accepted. And what happens is another electron is released from the other end of the battery to continue the circuit going. Now, what happens, therefore, is, you have this sort of cycle. That's why we can talk about batteries needing to be charged, because you need to generate something where you actually have these electrons to donate to the circuit. So this is what's happening. So we're going to try and work out what this is. What is sort of this method? Now, as a kind of aside, as these things do this random motion, they try and move, they're going to bump into these ions. That's what causes resistance. That's kind of one of the early models of resistance, is these things get in the way because and that's kind of so. What we're going to look at is you never need to draw that. Let's try and work out. Let's try and find out what is the how to find calculate the drift velocity. Okay, so we're going to need some sort of things. Okay, we're going to look. Here's our wire. Okay, and let's deal with a let's define a few things. That's a terrible drawing so far. Let's do it. So what we have is we've got our metal wire. It's got a cross-sectional area of A, and it's got a length of L. Okay, and in it we've got some electrons, and they're sort of being encouraged to move that way. Okay, that's the encouragement by the thing, which obviously means that the actual circuit, the current is actually going in this direction. I is actually in that direction, but our electrons are moving that way. So what can we do? Well, what's going to affect, what is going to affect the current? Our current is in many ways going to depend on several things. It's going to depend on how many of these things there are, like how many of them, and how fast they're moving. So let's think about, what this sort of means. Okay, so this is like, how. First question we've got to answer is how many electrons Oh, that's question one. Problem is that that's going to depend a lot on how big this wire is. The longer I make this and the bigger I make it, well, the more of them there are. So that doesn't really help. So actually, we turn this question into something slightly differently, and we have to therefore ask the question is, what is the free electron density? So we're going to ask, per cubic meter of this stuff, how many electrons are free to move in it? And this gets given a symbol. It's called N. Okay. Now you'll be given N, but we can actually work it out. Okay. Let's do a little example. If we wanted to find N, let's work out what is N for copper. Okay. Now copper is one of the best conductors. I need to know it's So copper. So, well, the way to answer this, copper. Sorry, I did just look at it. So copper has a density of 8,940 kilograms per cubic meter. Okay, so if you had a 1 cubic meter long, wire, so you had a wire with a volume of 1 meter cubed, then there would be 8,940 kilograms of copper. It's a lot of copper, to be perfectly honest. However, the molar mass of copper, so the molar mass of copper is equal to 64 grams. So if I had this sort of if I decided that this, that this weird wire was 1 cubic meter of copper, well, I'd actually be able to work out how many there would be, because I just need to know how many atoms of copper are in this. And if I know how many atoms of copper are in it, well, and I assume that one atom gives me 1 electron, then that actually gives me the same answer. So we end up with is this. Okay, so the number of atoms is equal to the number of moles. If you aren't doing chemistry, if you thought I'm going to get rid of moles, I'm never going to have to worry about it again, times the sort of Avogadro's number, which is 6 times 10 to the 23. So what that is, well, our number of moles is just this number divided by this number, recognizing this is in kilograms and this is thing. So if I had, 1 meter cubed equals 8,940 kilograms. So if I take 1 cubic meter, draw it out into a wire, I've got this number divided by this number. So I end up with 8,940 over 64 over 1,000 times 6.0 times 10 to the 23. I'm going to get a huge number. Okay, so I get 8,940 over 64. I get approximately 140,000. This part here, about 140,000 moles is what I've got here, times 23. And that gives me about 8.4 times 10 to the 28. And that is the number of atoms of copper there are in this weird cubic meter. If each atom gives me 1 electron, well, that also means that therefore my, this actually is also equal to my free electron density. Okay, this is how many electrons are free per cubic meter for copper. It's 8.4 times 10 to the 28 electrons per cubic meter. And that's one of the reasons why copper is a great conductor, because you can do this for lots of other metals, and this is kind of one of the ones at the top. It has a very large number of free electrons. Metals tend to have free electron densities in the region of 10 to the 28. That seems to be a thing. Insulators, by contrast, will have almost none, because there won't be any free ones, so there isn't anything there. And semiconductors will be somewhere like about 10 to the 18. So a big number, but 10 billion times less. So free electron densities for metals, this is a good number, this is a big number. So we can get an idea. You don't have to repeat this kind of equation thing, but we can, but it isn't that hard to calculate. It doesn't involve huge amounts of steps. Actually, the only real step is saying I get 1 electron per atom, which is a decent approximation. And so we actually are able, by knowing the molar mass things, we're able to measure that, and that's the thing you get given. So first step is, can we do that? Yeah, we can. So we can know, so we can actually also define N, which is, the free electron density which is per cubic meter. So that's what we got there. So, okay, let's consider what else we know. We know the charge on each electron. Okay, we know the Q on each electron is just equal to E. That's what we know, and we know that the current, magnitude of the current, let's ignore the fact it's going the other way, is equal to delta Q over delta T. That's what we know. Okay, so let's think about what we can do with these bits of information. Okay, so we know, I'm going to redraw it just down here. So what we know is we have a cross-sectional area of A, we've got a length of L, we have a current value which we can measure with an ammeter, okay, which is equal to that. We have an N which we can know, and we have a charge on an electron which we know. These are the things that we know, and we want to find out V. We want to know how fast they're going. So let's deal with what we can do. So step one, what is the volume of the wire? Well, that's equal to A times L. This area times the length. Okay, not even doing pi r squared h, because I don't really worry about that. So A times L. There we go. There it is. So next question is, how many electrons? Well, this number, n, which we'd be able to work out, that's the number of electrons per volume, and this is the volume. So we've got n times A times L. Okay, step 3. So therefore, how much charge is free to move? Okay, what is basically Q? What is the charge that's free to move that's inside this thing? Well, it's just N times A times L, which is the number of electrons, times the charge on the individual electron, NaLe. Fantastic. Right. So now we ask ourselves a question of, well, we want to know the rate of flow. We want to know how much time will it take for an electron that's right at this end, this first electron here, okay, call them Bob. How long does it take for Bob to get all the way over there, given that they're moving that way with a drift velocity of v? How long does it take them? Well, it's just speed, distance over time, okay? So the time for all of the electrons that are currently in this, say, at one moment, the time for all of them to move through this surface, because say that's where we're going to stick our ammeter, well, is distance, L, over time, over speed, v. So the time for all that charge to pass through the cylinder is T is equal to L over V. So therefore, what is the rate of flow? So therefore, the rate of flow of charge is the total amount of charge that's in the thing divided by the time it takes to move. So it's this bit divided by this bit. Okay, is delta Q, the amount of charge over the time. So that's going to be equal to NaLe over L over V. Oh look, my lengths are going to cancel out. I can use my rainbow for that. And my V is going to go to the top. So that this. And what is this? Oh, this is just the current, the rate of flow of charge. The current is equal to NAV. And there we go. That is how we can get an equation that links things that we want to know. Okay, we want to know what the current is. Okay, well, we can measure current. That's good. We can work out by using ideas of moles about how big, how many electrons are meant to be in there. That's good. We can measure the diameter of wires. That's good. Okay, we know the charge on an electron. That's good. So the thing that we want to know, okay, is V. V will equal the current that we measure divided by NAE. That is the thing that allows us to work out the drift speed velocity of an electron in a wire of a certain current. And it kind of should make sense. The faster it's moving, the bigger the current's going to be. That's a thing that should hopefully make sense as a kind of concept. So let's deal with a kind of example, okay? And the kind of example that you might find, okay? So let's deal with a kind of thing. So let's say, and as an example, okay, we're going to deal with a copper wire of diameter 2 millimeters is carrying a current of, let's say, 0.8 amps. Okay, we can say that, what is the drift velocity? Of the electrons? Well, here we go. Difficult challenge here. Remember, this is a diameter. We need an area, and this is in millimeters because they're not big numbers. Okay, so step one is calculate the area is equal to pi d squared over 4 because we've been given the diameter. We'll measure these things when you get back in, so we can work that out. So we've got pi times 2 times 10 to the minus, one sec, what's that? That's annoying. Nothing's going on. Right, okay, 2 times 10 to the minus 3, and that's all squared over 4. So we can work that out. So pi times 2 to the minus 3 squared over 4 times pi. Excellent. We've got 3.14 times 10 to the minus 6. Meters squared. So that's our area. And then we want to do, secondly, let's say that V is equal to I over N times A times E. So that becomes 0.8 divided by N. Good news. We worked that out earlier. That was 8.4 times 10 to the 28. Times by the area. So we've got 3.14 times 10 to the minus 6 times by the charge of electron, 1.6 times 10 to the minus 19. Big number, and on to a thing, and let's work it out. So 0.8 over 0.4 is 28 over 3.14 is the minus 6 over 1.6 is the minus 19, and we get, excellent. Put that in the thing. I get 18 times 10 to the minus 6 meters per second. or basically 18 micrometers per second. And that's actually one of those things. I mean, you think about, you know, we often have this picture from when we look at simulations and things, and in our heads we think of electrons moving really quickly through wires and zooming around circuits and going back to that. And it's one of the models that's useful when you're, when you're trying to picture it, but actually it doesn't happen. I mean, the lifetime of many many sort of like batteries, even if that once that battery, I mean, it's barely moved most of those electrons at all. They haven't moved very far. If you had a 1 meter long wire, so let's say your wire was like 1 meter long, how long does it take you to move at this speed? If you're going at 18 micrometers per second to move 1 meter, it would take you 52,752 seconds to do this sort of 1 meter journey. So divide that by 3,600. It takes you 14 hours to just do that single meter. So electrons, although their random velocity is high, they're not going anywhere. But in a wire, they really don't go very fast at all. But that is how we work that out.